In this video, we're going to take a qualitative look at what do we mean when we say small signal. And so in order to facilitate this discussion, we're going to consider a simple amplifier circuit that we've seen before. So here we have explicitly separated our AC source and our DC source or battery. And so as we said in the previous unit, really it'd be better if we had some kind of coupling capacitor, but we're going to ignore that for now, and let's just say we have them both connected in series to the base, as shown here. And so, of course, that V of S is our AC input. So because we have this V of S, which is our AC input, we're going to have some component of our base current, which is going to be AC as well. So we're going to have some AC base current. And so our notation is going to be lowercase I, lowercase b. Well, if we have an AC component of our base current, well, our collector current is just beta times IB, again, assuming we're in the forward active mode, then that means we're going to have some AC component for our collector current. So AC collector current. And so again, that's going to be I, lowercase c. Well, if we have an AC collector current, then we're going to have some AC voltage drop across our resistor RC. So AC voltage across our resistor RC, and ultimately what that means is we would have some AC voltage at our output. And so in this case our output is the same as the voltage VCE. So AC voltage at our output, VCE. And so ultimately, remember, we could say that in general the circuit signals are going to be superposition of AC and DC. So in general, what we have then is we would have a base current, which is lowercase I, uppercase b. So this is going to be our total instantaneous base current, and that's going to be equal to some DC component, uppercase I, uppercase b, plus our AC component, which is lowercase I, lowercase b. So a similar thing for our collector currents. We have some total collector current, which is equal to a DC collector current plus an AC collector current. Of course, some letters are hard to tell if it's uppercase or lowercase, C and S, for instance. So we'll kind of have to use context clues or check in the notes to see what one we're talking about. We can talk about a couple other quantities as well. So we said we can also talk about our VCE. So this can be defined as some DC collector emitter voltage plus some AC collector emitter voltage. And then finally, we can also talk about our base emitter voltage. And so really this is going to be true for any signal though, but the last one I want to focus on is our base emitter, which can have a DC component and some AC component as well. And we remember though that for this to be true, we're using superposition, so we need to have a linear relationship. So for this to be true, we are assuming that our AC signals are small enough. Let's see, clean that up a little bit, getting ahead of myself. So assuming AC signal is small enough such that we have a linear relationship, or such that linear relationships hold. And so ultimately what that means is that we can do our quote-unquote small signal analysis. So then the question becomes, how small do we need to be in order to do small signal analysis? So how small for our quote-unquote small signal? And so again, this is what we're trying to get at in this video qualitatively, and we're going to come back in the next video and look at it more quantitatively. So in order to sort of get a good starting point, let's recall that that base emitter junction is really just like a forward biased p-n junction diode when our device is in forward active mode. And so I've got here sort of the makings of a plot for our base current, and notice this is our total base current, and that's plotted against our base emitter voltage. Again, the total instantaneous value consisting of AC and DC values. So if we know that it behaves like a diode, we're going to have something that looks like this. And so let me make this a little bit thicker. So remember, we have some exponential relationship after the cut-in voltage, so we get something that looks like this. And so what we're saying is, of course, we have some operating point. So from our DC biasing, so in the circuit above, that's going to be our VBB and our VCC, we're going to have some DCQ point. So we'll have some DCQ point, and that DCQ point is going to correspond to some values of our base current, so we can call this IBQ, so our base current at the quiescent point, and we can call this voltage down here our VBEQ. And so what we're saying though is we know we have some AC component on our base current. So we said because we had that V sub S AC source, we have some AC component on our base current. So what we can think is that on sort of superimposed on that IBQ value, we're going to have some type of AC signal. And again, we're considering sinusoidal signals. So we have something that looks like this over time. And so of course what that is going to do is that's going to create an AC signal in our base emitter voltage as well. So over time we'll get something that looks like this in our base emitter voltage. So that's as time is going this way. And so sort of qualitatively, what we're saying when we're considering small signal analysis is we're saying we don't want to have to deal with that ideal diode equation, but instead what we want to be able to do is we want to be able to come in here with a linear approximation and say at this Q point, if I put a linear approximation, is that going to be a good enough sort of match? So this red here, so let's go back to here and say this red is a linear approximation. And so it turns out that our AC signal, so what do we mean by small signal? So qualitatively, small signal is small enough when that linear approximation is an appropriate representation of our actual curve represented by the blue curve above. So small signal is small enough when our red line, which is our linear approximation, is good approximation for our blue curve. And so again, as I said at the start, we were just setting out to look at this qualitatively. And so we can see that, of course, if we have small deviations about that Q point, then that red line is a pretty good approximation. Now, if we were to extend that out to here, for instance, and we see up here, yeah, maybe that's not such a good approximation. In the next video, we're going to come back and we're going to take a closer look quantitatively at what needs to be true in order to use this linear approximation. One other thing I want to make a note about is the slope of this linear approximation is something that we're going to come back to later. And so it turns out that the slope of this is 1 divided by r pi. And again, we're going to come back to this slope and this r pi parameter later, and it's going to be pretty critical in one of our models when we're doing this small signal analysis.